So let's introduce our new subunit 2, and that is none other than reflection of light at a curved surface. So this is our subunit 2. Don't forget, subunit 1 was reflection of light in a plane mirror or a plane surface. We have analyzed the number of stuff. Now we are here on this next unit, subunit I mean, that is reflection of light at a curved surface. Okay? So before we move far, we would like to know what is a curved surface first of all. Okay? What is a curved surface? So we can say a curved surface is a surface formed from a transparent sphere. Okay? So if we have a transparent sphere, let hope you know what a sphere is in shape of a ball. Okay? If we have a surface which is transparent and is spherical like a ball, and we so happen to catch something very small circular, what will come out is what you're calling curved surface, which will bring, if we paint it, it can bring what we're calling a curved mirror. Like if I have a surface like this, if I have this sphere, just like a ball, and I happen to remove, imagine on a ball, you remove something like a something circular on a ball. Huh? Imagine the ball is like some glass kind of something transparent, and then you remove something circular on it, round like this as it's curving. Yeah? So you will be having something like a plate, yeah? Something like this. Okay? So depending on which side you're going to paint will give us which type of mirror we are talking about. If you remove it and then paint this other side, you're forming what we're calling a concave mirror. If you remove it and then you decide to paint the inside side, we shall be forming what we are calling a convex mirror. So if at all they ask you to define what a curved surface is, curved surface is a surface formed from a transparent sphere. So having known what a curved surface is, let's look at, if it is formed from there, what are the types of curved surfaces? Types of curved surface or a curved mirror, to be more specific. One is the diverging, isn't it? The concave. I can call it concave mirror, which is as well as known as a converging mirror. Okay? So we have a concave or converging mirror. We shall say, what is a concave mirror? We shall say is a mirror formed from a transparent sphere by silvering by silvering a side opposite the center of the sphere. In bracket, or is a mirror whose reflecting surface, a mirror whose center of sphere C is in front of the reflecting surface. That one can be simple definition of what we're calling a concave mirror. It is a mirror formed from a transparent sphere by silvering a side opposite the center of the sphere. Or it is a mirror whose center of sphere is in front of the reflecting surface. So what do we mean? That if I have a sphere like this, spherical, and then I happen to remove this, I cut this circularly. What happened is this sphere here initially had a center. So if I happen to shade this other side here, okay, I'm shading the outside, in that the inside is left, or in that the center of the sphere remains in front of the reflecting, because if I shade here or if I silver this outside part, I'm leaving the inside, and now the inside is going to act as the reflecting surface. Therefore, the reflecting surface is now the center of the sphere is now in front of the reflecting surface. If we so happen to do that, we call that one a concave mirror or a converging mirror, that all the rays coming to it, it converges it to a common point. So we can have a simple sketch for that. It is something like this. If I have that, this is my mirror. This could be the center of curvature. This can be the focal length. So it is a converging, in that if rays come here, they are reflected here. If rays come here, they are reflected there, and then passes through the focal length. And this point P will be acting as our pole. This kind of mirror here is what we are calling a concave mirror. Is what we are calling concave mirror. This distance here with them, we shall call it R, radius of curvature, and then this distance here with time we shall call it F as the focal length. Then the point, that is the focal length, this is the pole, something of the kind. So a simple diagram representing our concave mirror is like that. And then let's look at the second type. That is none other than the convex mirror, which is the same as the diverging mirror. This one, in simple understanding, you can say is a mirror formed from a transparent sphere by silvering the side. If the other is opposite the center of curvature, we can say silvering the side in front of the center of the sphere. Or you can simply say is a mirror whose reflecting surface is a mirror whose center of sphere, whose center of sphere is behind the reflecting surface. You can define that and say that a convex mirror is the type of mirror where you would find the center of the sphere for which it was a part is in the front or is behind the reflecting surface. Is that okay? So what do we mean in this case here? That if I have something like this, okay? This mirror has a center here. And you realize that in this case here, we try to paint here. The reflecting surface is this side and the center is this side. That means that the center of the sphere is behind, isn't it? The reflecting is here, but the center is behind. The reflecting is here. The reflecting is here, but the center is behind. Whereas this one reflecting is here, the center is here in front. Okay? So that is what we are calling a convex mirror. And here what is very true is that if the light rays come, they are incident here, they are reflected here, and appear to be coming from some point here. Here it is incident, and then reflected, appear to be coming from some other point here. Okay? And now this is acting as our F, and this point here, this legs here, is what you're calling F. And then we can have here our point C here, such that this one can act as our R. This is the pole. You can call A, B, which is the length of the surface of the mirror, and that's the aperture. Okay? So, with those two are our types of curved mirrors. So whenever they ask you types of curved mirrors, we have basically two. We have the concave and the convex. And when we talk about the concave, a mirror whose center of the sphere is in front of the reflecting surface. The best drawing is there. The reflecting surface is inside, even now the center is in front of it. But here we're saying a mirror whose center of sphere is behind the reflecting. So that means that the reflecting is here, but the center is behind. That is our convex mirror. That is our convex mirror. So let's look at properties. Let's look at properties of the curved mirrors. Properties of curved mirrors. Properties of the curved, or you would even say some simple terminologies that we can basically use here. Properties of curved mirror. Curved mirrors. So to analyze the property very well, I would beg we look at this kind of drawing here. We look at this here. Okay, you can look at that if that is F, and this is Z. And then I do some naming using this. I can now call this one F. I can have a point here, call it C. This is A, P, B. Okay? And then I can call this one here. I can call this one F. I can call this one here R. Is that okay? So we can use that simple drawing of ours to represent, to try defining some simple terms. So we can begin with one center of curvature. And on our diagram it is C. Okay? What is the center of curvature C of this mirror here? We can define it as is the center of sphere for which the mirror forms a part. So the center of curvature, it is the center of the other original sphere for which the mirror was a part of it. Is that okay? That we had a sphere like this, and now its center was here, and now we decided to cut that mirror, okay? That sphere, to get a mirror from it. So it is the center of the original sphere from which the mirror came from. That is what we are calling the center of curvature. And then after looking at center of curvature, let's look at radius of curvature. Radius of curvature R. Isn't it? What is the radius of curvature? Radius of curvature, we can also say, it is the radius, it is the distance from the pole to the center of curvature, to the center of curvature, or in bracket, to the center of the sphere, or to the center of the sphere, for which the mirror forms a part. In other words, I'm trying to mean it is the distance from the pole to the center of curvature. So now we have talked about the pole. What is the pole? What is the pole? Pole is point P on our diagram. Pole P is the midpoint of the curved surface. The midpoint of the curved. Okay? So what we are meaning by the pole, which is this point here, it is the midpoint of the curved surface. The middle is what we are calling the pole. And then let's look at another thing that is now, I can maybe say, let's look at number 4. Let's look at number 4, focal lengths. Focal point first, and then Roman 1, concave mirror, because because the focal point, the definition will depend on which type of mirror are you referring to. So what is the focal point? Capital F. We use capital F to denote focal point. Okay? So we can define it is the point along the principal axis. Is the point along the principal axis where all rays which are originally close and parallel to the principal axis converge after reflection in the mirror. Okay, so that is what we are talking about as the focal point for concave mirror. It is the point along the principal axis where all rays which are originally very close and parallel to the principal axis, they converge after reflection. And then let's look at Roman 2 for convex mirror. Convex mirror. For convex mirror, we shall define it as it is also the point along the principal axis where all rays which are originally close and parallel to the principal axis appear to diverge from after reflection in the mirror. Please, the definition seems to be the same, but trust me, they are not the same. Very important here is you should master this here. Appear to diverge from after reflection. Appear to diverge from after reflection. But here we say that it converges instead. Okay? Converges after reflection. Is that okay? That if it is for convex mirror, like this, if it comes, it will be reflected, isn't it? But as it's reflected, it will be seen as coming from some other point. The point where it is seen coming from is what we are calling focal point. That is for convex mirror. It appears like, but it is not true. It appears like it is coming from that point. It appears like it is diverging, moving away from that point. But we're saying for concave mirror, it is very true that if they come later on, they converge to that very point. Is that okay? So that is for concave mirror. And then let's look at another term. Let's look at now focal lengths. Focal lengths We can just now simply say focal length is the distance from the pole to the focal point. As simple as that. Or if you want to define it in big words, you can say if it is for concave length, for concave mirror, you can say it is the distance from the pole to the point along with the principal axis where all rays are. Yeah, you make that law statement. Or you can say that it's the distance between the pole and the focal point. Is that it? Or if you want to be more specific with which focal point you are meaning, you can break it down and say, if it is for concave, you say it is the distance between the pole and the point along with the principal axis, where all rays which are originally close and parallel to the principal axis converge after. That is when you want to mention this. If they say define focal length for maybe a specific mirror like concave. Is that okay? So you would definitely say, if they say define for concave, you say it is the distance between the pole and the, instead of defining focal point, instead of saying and the focal point, instead you bring the definition of the focal point if it is a concave mirror. If it was convex, you say and the point along with the principal axis where all rays which are originally close and parallel to the principal axis appear to diverge from after reflection. That is when you're trying to eliminate this, writing the whole definition, because this will be for this, and then this will come for, you eliminate focal point, because the whole of this is standing for focal point of a concave. The whole of this is standing for focal point for convex. So you can delete that word by rewriting all this and the point blah 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 up to there, and then the same for that. And then let's look at some other interesting term as well. We can look at number 6. Let's look at this is focal length F. Let's look at aperture. Aperture is represented here by APB. So if the length of the curved surface of the mirror. Is that okay? So that one would be our aperture. This length here from here up to that point is what we're calling the aperture. And then we can also maybe look at what we are calling a paraxo ray. Paraxo rays now. These are now the terms. Basically, we are now looking at the terms we shall be using in this kind of idea here. So what are paraxo rays? You can say these are rays which are parallel and close to the principal axis and subtends small arrows, isn't it? With it. after reflection. Okay? That is the paraxo. Rays which are very close. If I have this and then that, these rays which are too close to this are what we are calling a paraxo rays. We are calling them paraxo rays. So then let's look at marginal rays. Let's look at marginal rays as we are finalizing the terms. Marginal rays. So these are rays which are parallel but far away from the principal axis and subtends a bigger angle with it after reflection. So what we are meaning by marginal rays, those are rays which are far away from the principal axis, and what is very true with them is that for them they subtend bigger angles. So if I have my drawing like this as an illustration, if this is my surface, if I have this will be reflected here. But if I have this, will be reflected here. So you realize that this is what we are calling the paraxo, very close. The angle they subtend there is too small after reflection with the principal. But these marginal which are far away will subtend bigger angles. So these ones are called marginal and these ones are the paraxo rays. So lastly, let's look at what we are calling the principal axis. That is number 9. Principal axis. Can say this is a line joining the pole and the center of curvature. So what we are calling the principal axis is that when I draw this, we said the pole is the midpoint of the midpoint of the curved surface, and then we said that our center of curvature is the center of the sphere for which the mirror is the part. So when I draw a line joining those 2 points, we give that line there a name, principal axis. So these are the basic properties of some terms that are used in curved mirrors. So we pick up from there in the next episode.